Hello everybody, it's Mr. Pope from Wilmington Grammar School for Boys, and in the 7th calculus session, is this calculus 7? Pretty sure it is. We're going to be looking at integration by substitution and variable separable differential equations. Okay, what I'm going to be showing you now is pretty important. To be able to manipulate integrals using substitution, probably the most ubiquitous tool you're ever going to see. So vital. And to start off with, let's suppose I've got an integral and we could do indefinite integrals, but let's say a definite integral, so it's between a and b, and let's say this is some function of x dx. Then, to be able to write this as a different function, let's say this is now between p and q, and this is some function g of a different variable, let's say t, and this is integrated with respect to t, there's three things you need to change. And I've said this before. First of all, you need to change the limits. Okay, now these limits are in terms of the variable at the end, dx. Okay, so this dt is an indication that this is saying that t equals to p and t equals to q. Okay, so one, the limits need to change. And by the way, this stuff, integration by substitution, if I was going to categorize it, this is in the normal A-level maths section, and this is integration by substitution. You technically learn about this stuff in year 13. So powerful though. The next thing you would, one of the other things you would try to deal with is the integrand. Okay, the integrand is just the thing that needs to be integrated. And then finally, the differential bit at the end. Differential. Okay, so with the limits and the integrand, this just gets reevaluated with some clever substitution. Okay, just as how you'd expect. The differential part, we need to swap out using the chain rule and by differentiating the substitution choice. Okay, so you're probably thinking, right, okay, what do you mean? Well, let's go for an example of that. Let's suppose, e.g., suppose I want to integrate between 0 and pi over 2 sine of x times by cosine of x dx. And I want to evaluate what this thing is. Right, one of the hardest things to spot, okay, one of the hardest things to spot is, so nota bene, is the hardest thing to spot. The hardest thing is to spot the substitution. And for A level, the substitution is usually given because they just want to make sure that you understand the mechanics of what's going on. Okay, so here, suppose I wanted to solve this integral. Now there's various ways you could do it. You could use a trigonometric substitution because you know that sine x cos x is just a half sine 2x. And if you manage to spot that, then you know you've done enough on the trig work from this week and last week. But if you didn't spot that, you maybe need to go back and revise your trig identities. Another way we could have done this is by integration by parts, and you've seen that already. And then we're going to get some kind of loop, and then we'll need to close it by making this thing equal to, say, a letter like I. making I the subject and then evaluating. But now I'm actually going to do this by using substitution. So the trick is to spot if when you've got factors, so here we've got a sin x times cos x, does one differentiate to the other? Okay, now there isn't a unique substitution, but generally the most elegant one is if you can spot the integral in factorized form and you can see that one thing differentiates to the other. Now I know that sin x differentiates to cosine x. Why is this good? Because if I let u equal to sine of x, then if I differentiate with respect to x both sides, then u becomes du by dx, and sine x differentiates to cosine x. I'll then decouple this differential down here to bring the dx over to here, like so. And now this is what I mean when I talk about using the chain rule with the differential bit. I now know that wherever I see cosine dx, I can replace it with du. Well, cosine dx is just cosine times dx, so I can replace that bit with just du. So that's good. So I've got an integral of du times by, and I know what sine x is, that's just u, because we defined it to be that way. So now, just by doing that part, I've actually worked out what the integrand is and what the differential bit is at the end. I just have to work out what the limits are. And this is fairly easy as well. Remember, these limits, if it's ending in dx, then this is when x is 0 and x equals pi over 2. So when I substitute x is 0 into here, then sine of 0 is 0. So the bottom limit on the new integral is just 0. And now the top limit is when x is pi over 2, and sine of pi over 2, because we're working radians, and generally speaking we're always going to work in radians from now on, unless degrees are specified or heavily implied, sine of pi over 2 is just 1. And now, lo and behold, this rather disgusting looking integral with trigonometry and, you know, limits in terms of pi has now just become a really easy integral, and all I have to do now is integrate u with respect to u, so that's just u squared over 2, and evaluate this between 1 and 0. So this is just going to be sub in when 1, so I'm going to have 1 squared over 2 minus when I substitute 0 in, so that's 0 squared over 2. So clearly the answer is just 1/2. Okay. By the way, you can substitute back at any point in time. Like this, for example. Suppose this integral was here, but this time we don't know any of the limits. So this integral, suppose we wanted to do this. Suppose we wanted to integrate this. So we'll call this example 1a, and this is example 1. Then, by similar logic, I can use integration by substitution to show that in terms of u, it's the same thing here, right? We just ignore the limits for now. And then I integrate u with respect to u, it just becomes u squared over 2 plus a constant. And now I know what u is, that's sine of x, so I can replace u with sine of x, this becomes sine squared of x divided by 2, so it's a half of that plus c. So I can actually just work out indefinite integrals as well by back substitution, that's totally fine. Okay, I'm going to be doing lots of examples with this, so don't panic too much. I'm hoping that was fairly clear, but I'll go through some more difficult ones. I mean, I've got tons. I've literally got tons. I've got some step questions to come as well, so hang tight for them. But in terms of by substitution, really, as long as you do these three things, and it doesn't matter, so order in which you do them or evaluate them doesn't matter. However, I would probably start with the differential bit first, i.e. I've got my substitution and then differentiate it and see what happens. And also limits are pretty easy to do as well, because that's just a really straightforward substitution. Cool. Let's have a look at variable separable. So when I'm talking about variable separable differential equations, okay, this is in A-level maths. It's probably one of the easiest forms of differential equations you're ever going to find, and it's really simple. We'll have something like dy by dx equaling to, I don't know, some function of x times by a different function of y. Okay, and there's no real beef here. All you would have to do is you separate the variables. So just to make this crystal clear, let's make the y terms red and let's make the x terms blue. And all I'm going to do is to solve this. It's really easy. I take the y terms all on one side and I make sure the x terms are all on the other, and make sure the differential dy's by dx bits are not fractional. And then, because this is a nonsense and you can't, strictly speaking, decouple these differentials, to tidy it all up, just end this with an integral sign. And technically I divided by g, so this should be a 1 over gy dy. And you just evaluate the thing as you'd expect. The solution of this will be what's called the general solution to the differential equation. And when you integrate this, suppose you get some new function, I don't know, let's call, actually for argument's sake, let's say we've got the gy on the bottom there like that. And so that will mean this is actually just gy. Then what will happen is, let's say gy integrates to capital G of y, and f of x integrates to capital F of x, and all you need to do is put a constant on one side. So constant on one side. Why is it you only need to do it on one side? Well, let's suppose I have a constant on both sides. Let's call that C1 and C2. Then technically I could minus this C1 from both sides, like so. So that on one side I'll just have C2 minus a C1, which is itself just a new constant, which we'll call C. So really, when you've got an integral on both sides, you only have to put the constant of integration on one side, because you subtract it from the other side, and it's not necessarily the same constant of integration, so you're just going to get some constant term coming out. As usual, I'm probably going to go through an example of this. So let's try a really easy one, like dy by dx equals to, let's say, x over y. Actually, no, let's make it interesting. Let's have y over x. Okay, so example 2. Let's suppose I separate the variables, so I multiply by dx both sides to get y over x dx over here, and I divide by y to get 1 over y dy on this side. Then I integrate both sides, like so. 1 over y integrates to ln of y, and integral of 1 over x becomes ln of x plus a constant. And now this constant c I'm actually going to write as ln of a, because ln of a constant is still a constant. So ln of x plus ln of a, well, when you add logs together, you multiply the arguments, So you get ln of y equals ln of ax. And then when you exponentiate both sides, you'll get y equals some constant a times by x. Okay. And that's it. Why does this solution make sense? Well, what it's actually saying is, what does y equals ax look like? Well, y equals ax. Well, when a equals 1, you've got the y equals x graph. When you've got y equals 2, a equals 2, you've got y equals 2x. Oh, geez. When you've got, say, a is minus 1, you've got y equals minus ax, and so on. These are all going to be straight line graphs that go through the origin and just have a gradient of a. Why should this make sense? Because what this original differential equation is saying is that the gradient function is always just the y-coordinate divided by the x-coordinate. Is that true? Well, if we look in the case for the y equals x graph, suppose I pick this point here, which is the point 2, 2, then that's because I've gone too high and 2 along, and clearly 2 over 2 is just going to equal 1, which is the gradient 1 over x. And if I pick a different point, let's say there, 1, 1, this is clearly 1 up by 1 along, and that also has a gradient of 1. So it shouldn't be a surprise that any function of curves where the gradient is just the y-coordinate divided by the x-coordinate is just going to be any straight line going through the origin. Okay, now this is the general solution to the differential equation up here. Okay, so there's a lot of terminology there. This is a first order, and the reason it's first order because you have one derivative, right? If it was second order, then you would have like a d2y by dx squared. Okay, this is a first order variable separable because you can separate the variables. This is a first order variable separable differential equation, and we have found the general solution. Now, if I knew a certain initial condition or a boundary condition such that when x equals 2, y equals 1, then this would give a particular solution, and we'd know exactly what this constant a was. For example, when y is 1, this equals a times by x, which is at 2. So 2a equals 1, so a equals a half. So the particular solution would be y equals a half x. So if we were asked to solve dy over dx equals y over x, and it goes through the point 2, 1, then the general solution would be this, but the actual particular solution would be y equals a half x. Y equals a half x is the only function that behaves like this, i.e. as a derivative of y over x, and it also goes through the point 2, 1. Okay. Generally speaking, that's how you do variable separable differential equations. They get a lot harder, by the way, and generally speaking, for A-level maths, you just need to be really good with your trigonometric identities. You need to be able to manipulate partial fractions, stuff like that. For further maths, we look at things where there aren't variable separable, so we start looking at first order exact equations where we take advantage of the chain rule and we kind of work backwards. And we also have a look at second order differential equations by forming auxiliary equations of the form e to the mx or whatever the variable is, and taking advantage of the fact that e to a variable will never equal to 0, and then we form some kind of quadratic, and then we can derive forms of solutions. We'll get there when we get there, but for now, just being able to separate variables is your first step when solving differential equations. Okay, I've been yammering on for a good 20 minutes, and to be honest, we probably just need to do lots and lots of practice. So let's separate all this off. So all I've done so far is just some A-level maths. I haven't really looked at any further math stuff because I feel this stuff is fairly important. Can't go rushing it. So actually I don't need this page. I thought I was going to write more, but never mind. Okay, so if you want to try some integration by substitution, give this one a go. Pause the video, I'll do it in a second. Okay, so it tells you what the substitution is. Using the substitution u equals 2x to the 5 halves plus 1, or otherwise find an exact simplified value for this. Okay, so if u equals 2x to the 5 halves plus 1, maybe we should just work out what du by dx is. Well, 2x to the 5 fifths, to differentiate that we bring the power down, so 2 times 5 halves is going to be 5, x to the power of, and then we subtract 1 from the power, so 5 halves minus 1 is going to be 3 halves, and the plus 1 disappears. And now I can bring the dx over like so, and now I know that du equals 5 lots of x to the 3 halves dx. Okay, interesting. Right, so let's just have a crack now. So what are the limits? Well, when x is 0, I've got 2 lots of the square root of 0 and then raised to the power 5. That's what to the power of 5 halves means. Okay, so 0 to the power of 5 halves means I do the square root of 0 and raise it to the 5. We should be really familiar with that by now. I don't know why I'm talking about that. And then add 1, so clearly this is just going to be 1. Next up, when x is 1, then the square root of 1 and raised to the 5 is also 1, times by 2 is 2, add 1 is 3. So now the limits in terms of u are now 1 and 3. Next up, I have 2x to the 5 halves plus 1 in the denominator, which is exactly what I wanted u to be. Well, interesting. I've got 10x to the 4 on the top. Now, 10x to the 4 is actually 10x to the 8 over 2. And the reason I say that is because I just noticed that 5 halves and 3 halves add up to 8 halves. So I'm guessing, and this is the sneaky bit, if I let u minus 1 equal to 2x to the 5 halves, then 2x to the 5 halves times by 5x to the 3 halves still equals 10x to the 8 halves, which is 10x to the 4. Now I notice that I can split this 10x to the 4 as 2x to the 5 halves, which is u minus 1, and then times it by 5x to the 3 halves, and I know what 5x to the 3 halves times dx is, that's just du. And now I've got this, which is so much easier to integrate because this is just going to be between 1 and 3 of u minus 1 divided by u, so I can split this up into u over u minus 1 over u du. And clearly u over u is just 1, so when I integrate 1 that's just u, and when I integrate 1 over u that's just going to be ln of the mod of u. And now I just evaluate this between 3 and 1. So brackets, brackets, minus brackets, brackets. This is when u is 3, this is when u is 1. So when u is 3, I'm going to have a 3 there, minus ln of mod 3, minus, and then when u is 1, I'm going to have 1 minus ln mod of 1. Well, ln of 1 is just 0, and this 3 minus the 1 is 2, so it's just going to be 2 ln of 3. So that's my final answer for this question. And it wants it as an exact simplified value, and you can't simplify 2 minus ln 3 any further. Cool. All right then. So we've got a differential equation here. If you want to give it a go, You may need to use partial fractions here. Pause the video, give it a go. Okay. A population P in millions at a given time t years satisfies that differential equation. Initially, the population is 1/4 of a million. Okay, so what's that saying? Initially means that when time is 0, P is 1/4 of a million. Well, if P is in millions, that means P equals 1/4. So these are actually our initial conditions, and we're going to use them to find a particular solution to our differential equation. So this is variable separable. You should always, I've said this before, but integration and differential equations, there's not a standard technique. I mean, you have to, the hard part is being able to look at them and saying, right, this seems to be in the classification of equations I've seen before and I know the technique for. Like identification and application of correct methodology is important with this. You can't just go, oh, it's this, bang, and not think about it. So this is clearly variable separable. So if I get the p's on one side, this is going to be dp times by 1 over p times 1 minus p, integrate that, and multiply by dt, I'm going to have just the integral of 1 dt. Now you may see in some textbooks actually that it might be written like this, dp over p times 1 minus p, and essentially all that's saying is 1 over, it's just that, they're the same thing, they're exactly the same. I prefer writing it like this, I suppose, just because I like keeping the integrals separate. But if you're comfortable leaving it like this, that's totally acceptable. I'd probably argue it looks more elegant when it's like that. It takes up less space. I don't know. Maybe this is just me being primitive, but I like keeping the integrand and the differential bit a bit separate, especially with integration by substitution. Okay, so well, first of all, this thing here, whenever you're dealing with a fraction with multiple factors in the denominator, you're going to need to use partial fractions, just like I predicted. So you need to consider the function 1 over p times 1 minus p equals some constant over p plus a different constant over 1 minus p. I'm pretty sure a is 1 and b is 1 from here. Or is that true? 1 over p, 1 over 1 minus p. If I get this over a common denominator, p times 1 minus p, then I have to times this 1 by 1 minus p plus a 1 times p. The p's cancel. Yes. I did that by inspection. But suppose you didn't know that, what you would do is you'd multiply by the denominator here to get 1 equals a times 1 minus p plus b times p, and then you could let p equal to 1 so that you'll have 1 equals a times 1 minus 1, which is 0, plus b times 1, which means b is 1, and then I could let p equals to 0 by substitution so that 1 equals a lots of 1 minus nothing, which is 1, plus b times 0. Go back to the notes on partial fractions if you're unsure. If you haven't got to the point where you can just inspect and go, oh, okay, it's clearly this, then you may need to revise a bit more. But essentially, this is partial fractions. This should be fairly fine. So I now need to integrate this. So the left-hand side's pretty easy. 1 over p integrates to ln of mod of p. And this thing, well, does the bottom differentiate to the top? No. So what I really need is a minus there, but make that a minus. So this is actually going to be minus ln of the mod of 1 minus p, plus, and the integral of 1 with respect to t is just t, plus a constant. If I look on this side, this will be ln of the mod of p over 1 minus p. That's not a plus, that's an equal sign. Silly boy. T plus c. And now, if I exponentiate both sides, I'll get e to the t plus c equals to p over 1 minus p. And I notice that e to the t plus c is the same as e to the t times by e to the c, because you add the powers, and e to the c you can just call a new constant, which is a. So I'll now get e to the t times by a equals p over 1 minus p. And I want it in the form of 3p over 1 minus p equals e to the t. Well, if I divide by a, that's the same as timesing by 1 over a, and a is just a constant, don't know what it is, so let's just put the constant up here for giggles. Doesn't matter. I could put the constant at the bottom, it literally doesn't matter. Now, I know an initial condition, i.e. when t is 0, p is a quarter. So when t is 0, p is a quarter, we'll have e to the 0, which is 1, equals a times a quarter, so it's a quarter of a, over 1 minus a quarter, which is 3 quarters, times by 4 top and bottom over there. So I'll get a over 3 equals 1, so a equals 3, so then that means I can whack that into there like that. So actually I will get 3p over 1 minus p equals e to the t, which is exactly what we needed to show. Okay, show further that p equals 1 over 1 plus 3e to the minus t. Okay, so this isn't too difficult, this is just making p the subject. So if I have 3p and I multiply by 1 minus p both sides, so I have 1 minus p lots of e to the t, and I expand, so e to the t minus p e to the t, lol, pet, and then I add that term to this side, so I get 3p plus p e to the t equals e to the t. Take a factor of p out, so this is p lots of 3 plus e to the t equals e to the t, and I'll divide by that now to get p equals e to the t over 3 plus e to the t. Now we're almost there, but you'll notice there's some stuff going on that's a bit weird. So what we're going to do is we're going to times by e to the minus t top and bottom, because essentially this is just timesing by 1 because it's the same top and bottom. So e to the t times e to the minus t is e to the 0, which is 1, over, and then 3 times e to the minus t is 3 e to the minus t, and then e to the t times that, well, that's just plus 1. Now I believe we got the right thing, it's just this needs to be swapped round, and that's a cosmetic choice. Okay, show mathematically that the limit, so this is part B. Part C, show mathematically that the limiting value for this population is 1 million. Okay, so what does it mean by limiting? Well, what happens when t goes on for infinity? Well, you're going to get p equals 1 over 1 plus 3 e to the minus infinity. And what does it mean, e to the minus infinity? Well, let's plot the e to the t function. It looks like this, doesn't it? Goes through 1. Right, as t goes to minus infinity, then the e to the t output is going to tend to 0. So this thing here tends to 0. So the whole thing becomes 1 over 1 plus 3 lots of 0, which just becomes 1 over 1, which is just 1. So p is never actually going to be 1 million, or rather, the only way p is going to be 1 million is if you let time go on to infinity. And it's always going to be approaching it, but not quite. So the limiting value is just 1 million. Okay, part D. Find to 2 decimal places the time it takes for the population to reach 3/4 of its limiting value. Okay, well 3/4 of the limiting value of 1 million just means I let p equals to 3/4 and solve. So 3/4, which is p, equals to 1 over 1 plus 3 e to the minus t. Well, let's flip both sides. So that becomes 4/3 equals 1 plus 3 e to the minus t. If I minus 1 from both sides, this 1 disappears, and 4/3 take away 1 is 1/3. If I divide by 3, that becomes a 1/9. If I take the log of both sides, this becomes minus t equals the natural log of a 9th. And then if I divide by minus 1, then minus ln of 1/9 equals to t. And that minus can come up as a power, so 1/9 to the minus 1 is just 9. So t will just equal the natural log of 9. That's a calculator job. There's no way I'm doing ln of 9 in my head. I'm not calculating it either by using an expansion. That's just too lame. So what was the accuracy? I want it to 2 decimal places. So 2.197, the 7 will round the 9 up. So it's 2.20 million. So the value of p, no, whoa. It's the time. T is in years. So it's 2.20 years. Okay, it's to 2 decimal places. So it looks like this population will be at 3/4 of its limiting amount after 2.2 years. Interesting. Okay. Next one, quite a tricky integral. Pause the video if you want to. Okay. By using the substitution u equals e to the x plus 1, or otherwise find that integral. Well, it's told me to use this integral, substitution, sorry. So, you know, I might as well give it a shot. I mean, by otherwise just means you won't lose marks if you do it a different way. But to be honest, 99% of the time it's usually quicker to do it the way they want you to do it. You know, just give it a go. Worst case, you're not going to lose too much time. If I differentiate both sides, then du by dx, which to be fair I can skip and just leave as du, equals to the differential of that thing times dx, and e to the x plus 1 just differentiates e to the x. Okay, cool. So now if I look at this integral, there's no limit, so that's fine. And now if I look at the top, I've got e to the 2x minus 2e to the x, which is actually e to the x lots of e to the x minus 2, and this is all over e to the x plus 1 dx. Why is that nice? Because I've actually got e to the x times by dx there, which is exactly this thing here, so I know I can swap that out for du. So I know I've got a du there, all over. The e to the x plus 1 is the denominator, so I can just replace that with u. And now I've got to somehow get e to the x minus 2. Well, that's easy. If e to the x plus 1 is u, then e to the x minus 2 is just going to be u minus 3. Think about it. To go from here to here, I minus 3. So I just go from there to there, that's minus 3. So now this becomes u minus 3, like so on. And now this is actually an incredibly easy integral to do, because it's just going to be integral of u over u, which is 1, minus 3 over u, du. It's going to be really good because 1 integrates to u with respect to u, and minus 3u becomes minus 3 ln of u, like so, plus an arbitrary constant. And now this is really easy to sort out because I know that u is e to the x plus 1, so this whole thing can be substituted back as e to the x plus 1 minus 3 lots of ln of e to the x plus 1 plus a constant. Now this plus 1 thing can get absorbed by the constant, so I don't even need this plus 1 technically. So actually I've got e to the x minus the natural log of e to the x plus 1 all cubed plus some arbitrary constant. That will do. I don't think we can tidy this up anymore, so we'll just leave it like that. Cool. Really easy. Okay, differential equation. You can usually tell when they're differential equations because it usually means you have to read a lot of stuff, and modelling you just have to read and figure out what it is they want you to do. These generally are the harder ones for people to understand, but I promise if you just read it and do what it says, it's honestly not that bad. Okay, so pause the video, give it a go. Okay. There are 20,000 chickens in a farm, and some of them have been infected by a virus. Lol, how topical. Let x be the number of infected chickens in thousands. Okay, so please be aware. So that means x is 20 is the total amount of chickens, right, because it's in thousands. And t is the time in hours since the infection was first discovered. Okay, the rate at which the chickens are infected Okay, so what does that mean? The rate at which the chickens are infected. So the change in infected chickens with respect to time, that's the rate, is proportional to, so let's use the proportionality symbol, this ichthus, to the product of the number of infected chickens, okay, so that's x, and the number of chickens not yet infected. Well, what would that be? That would be 20 minus x, wouldn't it? Because it would be 20,000 minus the unaffected chickens. Okay, cool. Right, so how do we get rid of that proportionality symbol? Well, from year 8, year 9, whatever year you did it, to get rid of that, we just remember that you put an equal sign and you times by some constant k. Okay, form a differential equation in terms of x and t and a suitable proportionality constant k. Bosh, just done it by reading the question. Okay, when the disease was first discovered, 4,000 chickens were infected. Okay, so when t is 0, when we were first discovered, x, the amount of infected chickens in the thousands, was 4. And the chickens were infected at a rate of 32 chickens per hour. Ooh, so dx by dt is going to be what? Well, it's 32 over 1,000, right? Because we're in thousands. So because x is in thousands, we've got to divide 32 by 1,000. So dx by dt, it's growing slowly, well, not slowly, it's in thousands, of 0.032. Okay, so we know at t is 0, x is 4, and dx dt is 0.032. So there's our initial conditions. B, solve the differential equation to show that blah. Okay, let's go back to our differential equation and separate the variables. I don't need to get the k on the other side, so I'll just have 1 over x times by, 20 minus x dx equals to k dt. The right hand side is easy, that's just kt plus a constant. And the left hand side, partial fractions, we're going to have to deal with that. So let's consider 1 equals a lots of 20 minus x, where a is going to be the over x term plus b over the 20 minus x term. I'm skipping steps here, plus bx. Okay, so when x equals to 20, the a disappears and 1 equals 20b, so b equals 1 over 20. And now when x is 0, I'm going to have 1 equals 20a, so a also equals to 1/20. So, if you like, I can put these both as 1, but integrate them, and remember there's a factor of 1/20 coming out as the front. That's really important. Okay, so what's going on here? I don't need this anymore. This is like a thought bubble. I'll put it over here. Okay, how to integrate this? Well, 1 over x integrates, well, it's the same as we did before, right? The 20 minus x differentiates to minus 1, so I need to put a minus there, so that's still fine. In actual fact, let's not skip steps. This thing, oh, come on. Okay, so because I want to abuse the fact that if the denominator differentiates to the top, I know what that is. So this is going to become 1/20 of ln of x minus ln of 20 minus x. This equals kt plus c. Okay, right. Well, if I multiply by 20 both sides, I'll get 20 kt plus, let's say, a different constant c1 equals the natural log of x over 20 minus x. If I exponentiate both sides, I'll get x over 20 minus x equals 20 kt e to that thing plus C1 as the power, but as we said before, that's just going to be a new arbitrary constant factor coming out there because e to the C1 is just a new constant. And what does this want me to get it as? It wants me t the subject. Okay. So if I divide by that a, that's the same as putting an a here, because dividing by a constant is the same as timesing by a different constant. I don't know, let's not call that a, let's call that b. And then if I take the log of both sides, and this becomes 20 kt, and then all I need to do now is divide by 20k here. So now I've got t being this thing. Okay, couple of constants to work with first. Let's work out what k is. And we can work out what k is quite quickly because I know dx dt is 0.032 when t is 0 and x is 4. So I've got k times 4, which is 4k, times by 20 minus 4, which is 16. So actually k is going to be 0.032 divided by 4 and divided by 16. So it's actually 5 times 10 to the minus 4, wow, which is 5 over, that's 10, 1, 2, 3, 4. So it's 5 over 10,000. 10,000 divided by 5. So it's 1 over 2,000. Okay. So I know k is 1 over 2,000. Ooh, that's interesting. So this term here is going to be 1 over 20 times by 1 over 2,000. Is that right? Okay. So what is 20 times by 1 over 2,000? That's 1 over 100. So this is actually 1 over 100. And that's just going to become 100. So we've actually got t equals 100 of the natural log of some constant b, x, 20 minus x. Which is nice because we know where that 100's coming from now. We just need to work out what the b is, and apparently it's 4. But let's use our initial conditions one more time. We know when x is 4, t is 0. So we know that when x is 4, t is 0. Okay, so let's make that a 0. This is 100 ln of b times x, that's 4b, all over 20 minus x. 20 minus 4 is 16. So what have we got? We've actually got 4 over 16. That's going to cancel down to b over 4. And if I want to make b the subject, I just divide by 100. So 0 divided by 100 is 0. I exponentiate both sides to e to the 0 is 1. And now I'm going to have b over 4. So b over 4 is 1. That just means b equals to 4. So now we're going to have t equals 100 of the natural log of b, which is 4x over 20 minus x. I believe that's exactly what we wanted up here. Okay, rearrange the answer in part B to show further that x equals to that. Cool. Fine. So let's have t divided by 100. So divide by 100 is the same as times by 0.01 t. I'm doing that because I spot there's something like that going on here. And this is going to be the natural log. Let's make this part C. Natural log 4x over 20 minus x. Okay, exponentiate both sides is e to the 0.01t, and this is 4x over 20 minus x. Multiply by 20 minus x is we're going to have 20 lots of e to the minus 0.01t minus x lots of e to the 0.01t equals 4x. I add that x term to the other side to get 20 e to the 0.01t equals 4x add x times e to the 0.01t. Take x out as a factor, so this is 4 plus e to the 0.01t. This is still 20 e to the 0.01t. Divide by this thing to get x on its own as 20 e to the 0.01t all over 4 plus e to the 0.01t. And if I divide by e to the 0.01t top and bottom, I'll get 20 over 4 e to the minus 0.01t plus 1 equals x. And is that what we wanted it to be? 20 over 1 plus 4e to the negative, yes, okay. Fine, so that's done, square box. Part D. If a vet cannot attend the farm for 24 hours since the infection was first discovered, find how many extra chickens will be infected by the time the vet arrives. Okay, so T is in hours, right? So and T is 24. Okay, so x equals 20 over 1 plus 4 e to the minus 0.01 times by 24. Okay, that's just a calculator job. So 20 over 1 plus 4 times by e. Where's my exponential button on here? Exponential of minus 0.01 times by 24. So x will be 4.8333 and so on. Now it says find how many extra chickens will be infected. And remember that when t was 0, x was 4. So that means the extra chickens will be this minus 4, which is going to be 0.82333. And remember this is in thousands, so if I move this along 1, 2, 3, that's going to be an extra 823 chickens. So in that 24-hour window, an extra 823 chickens out of the 20,000 has been infected. Cool. Devil in the detail. Right. Oh, nice integration by substitution. If you want to pause the video, give it a go yourself. Okay, use the substitution tan of x equals half of minus 1 plus root 3 tan theta to find the exact value of that. Okay, so if tan of x equals 1/2 of minus 1 plus root 3 tan of theta, then let's think about this. Let's differentiate both sides with respect to theta, or just differentiate them. Tan of x will become sec squared x dx, and this thing will become, well, a half of minus 1 will just disappear. Then a half, when I differentiate it, half of root 3 tan theta will become root 3 over 2 sec squared theta d theta. Okay. Fine. Well, doesn't yield anything particularly useful, so we'll leave it as that. Okay. Right. Now, let's move on. Is that going to be useful? Okay, I'll tell you what, let's manipulate this to begin with. So I've got pi over 4, I've got 0, I've got root 3 over here. Now 2 plus sine 2x is 2 lots of 1 plus sine of x cosine of x, if I'm not mistaken. Okay, and this is dx. Okay, remember sine 2x is 2 sine x cosine x. Well, next up, I need a sec squared coming out of there. So what I'm going to do, actually, thinking about it, is I'm going to divide top and bottom by cosine squared x. The reason for that is because on the top I'll get root 3 sec squared x dx, which is great because now I can see this sec squared dx term coming about, because now I've got this coming out here. Whoops. This is still going to be between pi over 4 and 0. On the bottom, now think about it. If we divide by cosine squared, then I'll have 2 lots of 1 divided by cosine squared just becomes a sec squared x, plus, and then sine x cos x divided by cos squared. Well, we divide by cos x once, it's just going to become a sine x divided again, it's going to become a tan of x d of x. Okay. Right. Now you're probably thinking, okay, so how's that helped? Well, actually, if you know your trig identities, you know tan squared of x plus 1 equals sec squared of x. Okay, so the bottom actually is pi over 4, 0. Well, first of all, I'm going to take these constant factors out, and that's going to be root 3 over 2 there. Now this denominator is going to be sec squared of x, and the numerator is sec squared x, and the bottom is going to be sec squared, which I now know is tan squared x plus the 1, and then I've got another tan x in the middle, like so, dx. And now, I think you find we're ready to substitute things in. For example, I know that sec squared dx can be replaced with root 3 over 2 sec squared theta. So if I replace this dx with root 3 over 2 sec squared d theta, sec squared theta d theta, the top is going to be a 1, right? Because we replace sec squared dx with that, so that term disappears. This integral, root 3 over 2 there. Now let's have a little think about what's happening with the limits. So when x is 0, then this is going to equal 0. So we're now going to have a half of minus 1 plus root 3 tan theta equals to 0. So times by 2 to get rid of that. Add 1 divided by root 3 is tan theta. So theta, what's the inverse tan of 1 over root 3? I believe that's 1/6 of pi. So the new limit on the bottom is going to be pi over 6 for theta. And when I make it pi over 4, well, tan of pi over 4 is 1. So when 1 equals a half of minus 1 plus root 3 tan of theta, then if I times by 2, that becomes 2 minus 1 plus root 3 tan of theta. And if I add 1, that becomes a 3, so that becomes root 3 tan of theta. And then when I divide by root 3, I'll get root 3 is tan of theta, and that's just when theta is 1/3 of pi. So now the limits are now between 1/6 of pi and 1/3 of pi. Okay. Now, tan squared is on the bottom, but I've got tan up here. So it looks like I'm going to have to square this thing. So tan squared of x is actually 1/4 of minus 1 plus root 3 tan theta squared. Well, what's that going to be? It's going to be 1/4 of, this thing squared is minus 1 times minus 1, which is going to be positive 1, and you're going to have minus 2 root 3 tan theta, and then you're going to have a plus 3 tan squared theta, like so. Okay. What else is going to be happening? I've got quite a lot of things are happening there. So I'm going to have that. So tan squared plus a tan x. So this will become that plus a tan of x plus a 1. Well, actually, I know tan of x. Lol. Tan of x is just this bracket again, so that's going to be a half of minus 1 plus root 3 tan of theta. Then I add 1. Okay, maybe some things cancel, maybe they don't. Okay, let's deal with the constants. I've got a 1/4. I've got a half times minus 1, which is minus a half, and I've got a plus 1 there, so it's plus 1. Okay, now let's look at the tan thetas. I've got a 1/4 of minus 2 root 3. So I've got minus 2 root 3 over 4 tan theta. And then I've got a half of root 3 tan theta, so it's going to be plus root 3 over 2 tan theta. And then the tan squareds, I've just got 3/4 of tan squared there. Okay. Well, actually, 2/4 is just a half, isn't it? So actually, this is going to disappear. Now, a 1/4 plus 1 is 5/4. 5/4 minus 2/4, which is a half, is 3/4. So actually this whole thing tidies up to 3/4 plus 3/4 of tan squared theta. And this is actually 3/4 of 1 plus tan squared theta. And we know 1 plus tan squared is sec squared theta. So the whole numerator on this thing actually becomes 3/4 of sec squared theta. And you know what? Okay, look what's going to happen here. The √3/2 is going to come on the outside, and that's going to multiply it together. What's going to happen is √3/2 times √3/2 just becomes a positive 3/4. And then because we're dividing by 3/4 there, that's going to disappear. And look, the sec squareds cancel. So, oh geez, that is amazing. It's just cancelled down to just 1 d theta between pi/3 and pi/6. That's amazing, because then that's just going to be theta between 1/3 of pi and 1/6 of pi. So that's just going to be 1/3 of pi minus 1/6 of pi. So the whole thing is just 1/6 of pi. Wow, that horrible integral here just boils down to a 1 d theta thing. That's just amazing. So yeah, really, really worth it as far as I'm concerned. Integration by substitution is such a powerful tool. It's actually quite nice when you get it and you feel like, oh, I've cracked it. It's going to be really easy. Well, that's how I feel anyway. Okay, so I'm going to end with 2 step questions because I kind of feel like we've done quite a lot of calculus now that we can start looking at harder and harder questions. And bearing in mind, step questions are used they're for people who have got an offer to study mathematics or computing, some kind of field involving mathematics, and they've got an offer from, say, Cambridge or Warwick or Imperial or something like that, and maths needs to be tested. Please, please, please do not beat yourselves up over this stuff. Step questions, they're pretty much an aptitude test to sort out the A stars from like the A stars. Yeah, they're very difficult questions usually. So to get it in context, you have to answer 6 questions in 3 hours. This is one of those questions, and this is from the 2009 paper, step 1, Roman numeral 1, or I, and this is question 6. So bearing in mind step 1 is the easiest, then step 2, and then step 3 is considered the hardest. Yeah, this is generally, step 1 is usually A-level maths knowledge required, and that's it. Whereas step 2, you start looking at further math stuff, and step 3, you're pretty much knee-deep in further maths. So you've got 6 questions in 3 hours. So really, if you can solve a question in under half an hour, you're doing incredibly well. Of the people that take the test, I can't remember what the cumulative percentages were, but people getting 4 or 5 questions right would usually be getting grade 1s and grade S's. Getting a score of 100 pretty much guarantees you that you're going to be getting an S. Well, not guaranteed. I've seen a couple of years where it's 102 points. Each question's worth 20 marks, so 5 out of 6 would be 5 lots of 20, which is 100. To be honest, I've not seen a paper where 100 marks doesn't get you a grade 1 or higher. I think it's contentious whether it's an S. Some years, most years I've seen it actually, usually 90 something is an S. But yeah, put it this way, getting 5 questions right in 3 hours, what's that, 36 minutes a question? Yeah. But then you've got reading time, various other stuff. Anyway, I prattled on for long enough. If you want to give it a go, be my guest. But bearing in mind, if you spend 30 to 40 minutes on this question, don't beat yourself up. If it takes longer, then it takes longer. But yeah, don't expect to do this in a couple of minutes. I mean, maybe you can. Anyway, pause the video, give it a go yourself. Okay, so I chose this question from the questions by topic generator are for STEP, and I just looked up substitution, and here was one of them. So, polynomial substitution. So, just curious, how long will this take me? Okay, 105, so 5-minute mark. Show that for m is positive, that integral is the same as that one. Okay. Interesting. Well, what have I got? I've got the integral of m, let's see, 1 over m, x squared, and then this is x plus 1 over here, dx. Well, I'll be honest, you don't want to divide things. Oh, geez, really? Oh, man. Right, sorry about that. Okay, my Hoover just went off. So, how do we do this integral? Right, I can't remember what I was saying. Right, I don't want to divide by x plus 1, so let's try a U-substitution. Let's let u equals x plus... Oh, mate, what's going on here? X plus... Mate, what's going on? My pencil's being weird. X plus 1. Okay, this is nice because this is going to transform this into, well, when x is 1 over m, then u is 1 over m plus 1, and then this will become m plus 1 on the top. U minus 1 is x, so u minus 1 squared is x squared, so that'll be the u minus 1 squared on the top. The bottom is u. And then clearly if I differentiate the substitution, I'll get du by dx equals 1, or just du equals dx, so then I'll just get this. And now this is relatively easy to integrate because this is just going to be, well, the top expands to u squared minus 2u plus 1. And when I divide that all by u, I'm just going to have u, oops, I just have the integral of u minus 2u over u, which is minus 2, plus 1 over u between m plus 1 and 1 over m plus 1 du, like so. Okay, integrating u will just become u squared over 2. Integrating minus 2 becomes minus 2u. And integrating 1 over u just becomes plus ln of the mod of u. And this is between m plus 1 and 1 over m plus 1. So, evaluating this, we're going to get... now I'm going to do this individually, actually, to tidy up. So I'm going to have the m plus 1 squared over 2, but minus, and then I'm going to have the 1 over m plus 1 squared over 2. Then minus 2 lots of the u's, which is just going to be m plus 1 minus the 1 over m plus 1. And then plus, and then we're going to have the ln of m plus 1 divided by, because we're subtracting ln of 1 over m plus 1. Okay, right, if I look at this thing over here, I can take a factor of half out. M plus 1 all squared is going to be m squared plus 2m plus 1. And then if I minus all this squared, I'm going to have minus 1 over m squared minus 2 over m minus a 1. The 1's cancel. That's fine. And then minus 2 lots of, well, the 1's cancel here, and this is m minus 1 over m plus, and then if you think about it, 1 over m plus 1 is the same as m plus 1 over m, if I get it over a common denominator. So if I do m plus 1 over this, which is m plus 1 over this, then this and this cancel, and it's 1 over m, so the whole thing is just m, so that's ln of just m. Okay, right, let's tidy up. So, I've got 2m minus 2 over m, but times by a half. So I've actually got 1 lots of m minus 1 over m. But then I've got minus 2 lots of m minus 1 over m. I spot that. So these are going to cancel, and it's just become minus 1 of m over m minus 1 over m. And then I have m squared minus 1 over m squared, and this is times by 1/2. then don't forget the ln of m. Okay. What can we do here? Well, I notice when I do a half of this thing, I'm going to get a negative 1 over 2m squared. So maybe I want to get everything else over a common denominator. So when I do a half of m squared, I'm going to get m squared over 2. But if I want this to be an m squared, I'm going to need to make this to an m to the power 4, so that would cancel. Minus m. Now if I want this over 2m squared, then m times by 2m squared, that would be an m cubed. Has to be a 2m cubed, so I want that to be minus 1. And then that has to be a plus, and then for this to be a 2m squared, I have to have 2m squared on the top, like so. And then this will be plus ln of m modded. And now I can make this one big fraction all over 2m squared. So I'm going to have m to the 4 minus 2m cubed plus 2m squared minus 1 plus ln of m. And now if I look at what I'm trying to get, that's nice because I've got the plus ln m bit, I've got a fraction over 2m squared. Now I have to factorise that top thing, and then using the factor theorem, it's pretty obvious that if m is 1, that's a factor, because 1 to the 4 is 1, minus 2 lots of 1 cubed is minus 2, plus 2 lots of 1 squared is plus 2 minus 1. Well, they cancel and they cancel. So m equals 1 is clearly a factor. Fine. So we'll have m to the 4 minus 2m cubed plus 2m squared plus no m minus 1. Long divide that by m minus 1. So m's in m to the 4 is going to be m cubed. So that's going to be m cubed minus m cubed. So when I subtract that, minus 2m cubed minus minus m cubed is going to be a minus m cubed plus 2m squared. So that needs to be a minus m squared. So that'd be minus m cubed plus an m squared. So then subtract 2m squared minus m squared is going to give an m squared. Bring the 0m down. How many m's in m squared? That's going to be plus m. So that's going to be an m squared minus an m. M minus minus an m is m minus 1. And that's clearly going to be a plus 1. So that's that. No remainder. Okay. Well, that is interesting. So is m minus 1 supposed to be a factor 3 times? That shouldn't work out. What have I done wrong? I have done something wrong here. The reason why I can tell I've done something wrong is because if I substitute 1 into there, and then 1 into there, that's going to be minus 1, and then 1 into there is going to make that 1, and a 1 into there is going to make that a 1, and add these all together, the result is 2. It needs to be a 0 because we've clearly got multiple factors of m minus 1 in there. So I've made a boo-boo. Was it because I don't have the final thing properly? Oh god. No, this should have been a 2m. Yeah, because this needs to be a 1 over m, so that needs to be 1 bigger on the bottom. Okay, so this should have been a 2m, not a 2m squared. So actually, this is wrong, this is wrong. This should have been a 0m squared. This should have been a plus 2m. So I need to bring down a 0. So 0 minus m squared, that will become a negative m squared. So this needed to be a minus m. So that would be a minus m squared, that would be a plus m. That minus that. Ooh. Is that even working still? Oh dear. I feel I've made a mistake. That's fine. We'll scramble this. Right. I've rushed steps. I'm clearly not thinking. Right. Got plenty of time. There's nothing wrong with trying again. Let's have a look. So have I skipped some bits? I think this bit is fine. So I've actually got a half of m squared minus 1 over m squared. I've got half of the other things, that's plus an m minus 1 over m. And I've got minus 2 of m minus 1 over m, plus a ln of m. Just double check. 1 of them minus 2 of them, that's just going to be a negative of these. Fine. If I put that as a half, then this has to be a 2 and that has to be a 2. And if I put a half of m squared at the front, this needs to be an m to the 4, and this needs to be a minus 1, minus a half of, and then if this is going to be an m squared on the bottom, then this needs to be a 2m cubed, and this becomes 2m. So I'm actually going to have all over 2m squared, lots of m to the 4, minus 1, minus 2m cubed, minus 2m is plus 2m. So I'm going to have m to the 4 minus 2m cubed plus 2m minus 1. Okay, is that correct? Well, when m equals to 1, then I've got 1 to the 4, which is 1, minus 2 lots of 1 cubed, plus 2 lots of 1 minus 1, that's definitely 0, so that's okay. Now another thing we need to note is we wanted it to be m plus 1, so I should be able to substitute minus 1 in there, and that works. Well, m to the 4 would be 1 when I sub minus 1 in. Minus 1 cubed is minus 1, times by minus 2, that becomes a plus 2. 2 lots of minus 1 is minus 2, minus 1, so yes, that works. Okay, I'm just being a silly. And this is still adding ln of m. What I'm going to do this time, actually, is I realise this m plus 1 is a factor once. So I'm cheating a little bit. I'm going to long divide by m plus 1 into the numerator, which is m to the 4 minus 2m cubed plus no m squared plus 2m minus 1. And m into m to the 4 is m cubed. M cubed times this is m to the 4 plus m cubed. Minus 2m, right, these cancel. Minus 2m cubed minus an m cubed is minus 3m cubed. So then bring down the 0m squared. M into 3m cubed is going to be 3m squared, so that's going to be minus 3m cubed minus 3m squared. Subtract that, that's going to be 3m squared. Bring down the 2m. M's into 3m squared becomes plus 3m. So that's going to be 3m squared plus 3m. Minus that is minus m minus 1. That's clearly minus 1 lots of that. And luckily this thing here clearly is just m minus 1 cubed. Right, so now I do indeed have m minus 1 cubed times by m plus 1 all over 2m squared plus ln m. So yes, I do have the thing that they were asking me to find, so that's not a problem. I'll take all this stuff, I'll make it smaller, I'll put it there. So this is all part I. Okay, show by means of substitution that this thing equals that. Okay, well, first thing to spot is that we got x to the n's now, where n is just a constant. So, and the other thing to spot to help with the substitution, this is really difficult to see, is that the limits appear to stay the same. Now, if we were to do u equals to x, say, then that's not really going to help so much, because that's just going to give the same integral. However, if I let u equal to 1 over x, say, then what would happen is the limits would flip, and if there was a negative sign, we could use the fact that taking a negative factor out, things would cancel. So at least this will guarantee limits will be similar. So if I differentiate both sides, then du by dx is going to equal, well, what's it going to equal? In actual fact, I don't want some x squareds popping out, so let's make it more general. Oh man, really? Oh god, I'm going to have to pause this video again, my pencil's going to die. Okay, sorry about that. So anyway, what I was going to say is let's make this more general, because I notice there's xn's in there, and let's just say u to the n is the same as 1 over x to the n. And by the way, that's the same as x to the minus n, right? So if I differentiate both sides, u to the n would just become n lots of u to the n minus 1 du, and x to the minus n would become minus n lots of x to the minus, and then because I'm going down a power, I'm going to take a factor of minus 1 out to get n plus 1, like so, and then this is dx. Okay, this is nice because then I can divide by n both sides, assuming that n's positive, and it is, so we're allowed to do that. No, it's not. Well, let's assume that n is positive. And then I can divide by minus 1 to get the following. So x to the minus n plus 1 dx is that. And now what I'm going to do is I'm going to look at this thing here, and I'm going to tidy this up a little bit. And I'm going to take an extra factor of x out, because x to the n times by x is actually x to the n plus 1. And then this is going to be 1 plus, and then I've got to have that as a 1 over x for that to work. Do you see why that is? Because if I times these two together, I'd still get the same as x to the n times by 1. So why is this good? Because now this integral is now the integral of 1 over 1 plus 1 over x times by 1 over x to the n plus 1 times by... Oh, mate, get off. No, no, stop. No, no, delete, stop it, no, sorry, no, back in you go. Sorry, my robot vacuum. Right, okay, oh jeez, going very well. Okay, fine, so, right, where was I? Yes, now, this thing is the same as this thing, so I can now replace it with minus u to the n minus 1. And if u to the n is the same as x to the n x to the minus n, then this means u equals 1 over x. So now this integral is going to become 1 over 1 plus u, which is great. And then 1 over x to the n plus 1, I can now replace it with minus u to the n minus 1 du, and I can take this minus and put it on the outside, and I can move this u to the n minus 1, sorry, up here like so. And now the only thing left to do is put the limits in. So when x is m, u equals 1 over x, which is now m, so that means the top is 1 over m. And when x is 1 over m, then u is 1 over m, which is clearly just m, so m goes on the bottom. Right. And now I can use this minus sign to flip the limit, so now I have the integral between m and 1 over m of u to the n minus 1 all over 1 plus u du. And now this is exactly what we wanted to see up there in general, which is fantastic. Okay. So let's just crack on, shall we? Part 3. Evaluate the integral between 2 and a half of x to the 5 plus 3 all over x cubed times by x plus 1 dx. Okay, so the point of this question is we've got to use what we've seen so far. We could do integration by parts, but I think that would get a little bit messy. So what we're going to do is I spot the x to the 5 and x to the 3 are going to cancel somewhat. So if I split these integrals up as the following, so between 2.5 of x to the 5 over x, not squared, cubed, getting ahead of myself, x plus 1 dx, plus the integral between 2.5 of, 3 over x cubed of x plus 1 dx. Okay, a couple of things we can do here. One, I can take this 3 out as a factor over here, so that's fine. What else can I do? Well, the x to the 5 over x cubed, I can take this x5 out and that can replace that with an x squared, and that's a 1. Okay, that's nice. So now a couple of things are going to happen. I've now got the first integral up here. Can you see that? I've got an x squared over x plus 1. Oh no, sorry, I did the wrong thing. There was x. This should be an x squared, shouldn't it? Because x to the 5 over x cubed. Yeah, it's clearly going to be okay, fine. Right. And next up, if I look at this integral here, when n is 3, then I'm saying I can replace this with 3 2/2, and then I can lower that to a lower power, so this is, say, u squared over 1 plus u du. And now this integral is between 2.5 of x squared x plus 1 dx. Okay, so we've just been using the results we've seen so far. Because we're dealing with definite integrals that evaluate at limits, this u doesn't need to be a u, this could be any variable we liked, so we might as well just make it an x. And now I realise I've got 1 lots of my integral here and 3 lots of my integral here, so this is actually just going to be 4 lots of my integral between 2.5 of x squared over x plus 1 dx. And this is going to be 4 lots of, well, I know how to integrate x squared over 1 plus x, it's over there, so it's actually going to be m minus 1 cubed. So here, clearly I have m is 2, so 2 minus 1 is 1 cubed, times by 2 plus 1, which is 3, over 2 squared, which is 4, times by 2, which is 8, plus the natural log of m, which is 2. This is quite easy to work out, because if I distribute the stuff in here, then 1 cubed times 3 is 3, over the 4 and 8 will cancel, so that'll just become a 2. And 4 lots of ln 2, well, 4 ln 2 is the same as ln 2 to the power 4, and 2 to the power 4 is 16. So the answer for the first integral was fairly easy. It was 3/2 of ln 16. Okay, and for the second one, notice we can't do that trick anymore because it's now got 1 on the bottom rather than 2. But maybe we should try stuff going on here, for example. Why should we do that? Well, because let's write this integral out again. So I like step questions. They build and they teach you stuff and you work it out. So what have we got? We've actually got the integral between 1 and 2 of x to the 5 plus x cubed plus 1 over x cubed times by x plus 1 dx. Okay, so by similar stuff you can clearly tell that if we isolate the x to the 5 term, then it's going to be 2 to the 1 of x to the 5 over x to the cubed, which is going to be x squared over 1 plus x dx, plus, and then if we isolate the x cubed term, the x cubed terms are going to cancel, so this becomes 1 over x plus 1, plus, and then I'm just going to have 1 over x cubed x plus 1 dx. Okay, let's think about this really, really carefully. Now, let's start with the easiest one. This one is probably the easiest because that is just going to be ln of x plus 1 evaluated between 2 and 1. Okay, because the bottom differentiates the top, there's no trick to that one. So that one's done, that's fine. I'm going to look at this one next, and the reason for that is because if we look at what we did in this part of the question, I know that the integrand bits are the same. The only difference is I have to be really careful with what my limits are now, because they're not going to be the same. So I know that this is going to be some integral of x squared decrease a power 1 plus x dx. But now I have to think about the limits carefully. Because what was the substitution I did here? The substitution was u equals 1 over x. Okay, and be careful, there was a minus out in front. So I'll put a minus there to begin with. And then remember that u is 1 over x. So when x is 2, u is 1 over 2, so that's a half. And when x is 1, u is 1 over 1, so that's 1. Clearly, if I make this a plus, I can flop those limits over. So actually, this is just an integral between 1 and a half, like so. Okay, so now I've got 2, 1, and x squared 1 plus x here, and this is dx. Oh, this is great, because now I just need to find the area of this thing and add it to the area of this thing. And since the bottom limit here is the top limit here, I can combine these two integrals together to get the integral between 2 and a half of x squared over 1 plus x dx. And then that's still adding the ln of x plus 1 evaluated between 2 and 1 still. Oh, it's beautiful. Why is it I can do that? Well, because look, what's going on here is, suppose I've got a function like this, and let's say this is the function between a half and 1, and this is the function between 1 and 2, then this integral in orange is clearly the one between 2, 1, which is the area of this shaded bit here. And this integral here between 1 and a half in green is clearly this area here. So I can clearly just do that integral between a half and 2 because I'm just adding the areas together. And now, have we actually derived between half and 2 of what that thing is? I think we did, didn't we? It's this, isn't it? So that's actually 3/8 plus ln 2. So this thing is 3/8 plus ln 2 plus, and then we need to evaluate this thing. Well, it's going to be ln. This thing is ln of 2 plus 1, which is 3, minus ln of 1 plus 1, which is ln 2. So that's actually ln of 3 halves. Ln of 3 halves. Bish bash bosh together, we've got 3/8 there, and 2 plus ln 2 plus ln 3 halves. You multiply the bits in the middle, so it's actually going to be ln of 3. Okay, so how long did that take? That's difficult. Well, 20 minutes or so. It's pretty good going. Yeah, no, that's the kind of level you need to be working at for Cambridge stuff. Being able to spot integrals combined together, cancel down, it's really the thing. Okay, last question, I promise. So actually, this is from a step 3 paper, so this is supposedly harder. But having said that, though, it might not necessarily be. They're not directly comparable. But on average, the spread of questions, to be fair, they just cover further maths topics. It's not that, you know, to be fair, they might not necessarily be further maths. But, well, I think you guys have got enough knowledge to do this question looking at it, so that's probably why I chose it. So pause the video, give it a go yourself. Okay, so there's a lot going on here. The first part is sketch the graph of the function ln of x minus a half x squared. So if I've got y equals ln of x minus a half x squared, maybe it'd be an idea, okay, on my sketch, what is going on? Well, for a start, x has to be positive. Why is that? Because you can't take natural logs of negative numbers or zero. So I know that for sure my function lives in these two quadrants, quadrant 1 or quadrant 4. It can't be on the left-hand side of the y-axis. Okay, next up, what else can I infer? Well, what happens when x is 0? Well, you can't have x as 0. So I know that there's an asymptote here on the y-axis. X equals 0. So it doesn't cross the y-axis. Does it cross the x-axis? Well, that would be asking to solve 0 equals ln of x minus a half x squared. And that's not going to be nice, because then if we add it to both sides, so x squared will equal 2 ln x, which is ln of x squared. And essentially, we're trying to say, when does e to the x squared equal x squared? That's not a nice function to behave. We don't have techniques yet to solve that kind of thing. That's kind of like not something we're interested in. But we can do something else. What about minimums or maximums? Well, dy by dx, ln of x differentiates to 1 over x, and minus half x squared, I believe, differentiates to just minus x. Now, if I want to solve that for x is 0, then the left-hand side, this thing, well, that's actually 1 minus x squared over x equals to 0. And because I want this equal to 0, I only need the numerator to equal to 0, so either x is plus or minus 1. And since our condition was that x has to be greater than 0, then clearly x equals 1 is the only turning point. If you're interested, you can sub 1 into here. Ln of 1 is 0, and minus a half of 1 squared is minus a half. So I know that when x is 1 and y is minus a half, I have got a point there, and it's either a maximum or minimum. What else can I infer? Well, I could find the second derivative, d2y by dx squared, and 1 over x becomes minus 1 over x squared, and minus x becomes minus 1. Clearly, at the point, the second derivative, at the point x equals to 1, is just going to be negative 2, so this is a maximum. So we've got some kind of rolling Archie type thing like that there. So it should be pretty obvious now that this is now going to hug the y-axis like so, and from then on it's going to disappear off to negative infinity like that. And at this point here, this is the local maximum at 1 comma minus a half. Not a lot you can do there. How do I know it's disappearing off to there and not flattening off? Well, let's suppose, I've got ln of x minus a half x squared. The logarithmic graph goes through 1 like that and then slowly goes to infinity. It's quite slow. Whereas the minus half x squared graph is going to be a U-shaped parabola looking like this. As x goes to infinity, clearly this function is winning, if you like. It's getting negative quicker. If you'd like, you can take derivatives of the individual things. For example, the derivative of ln x is 1 over x, and the derivative of half x squared, if you like, is just x. So for what values is the magnitude of these things greater than that? Well, clearly for x being a positive number, then x squared has to be greater than 1, which means x is greater than 1. So pretty much after that minimum point, the minus half x squared function always wins, And so that's clearly going to be a number minus a much larger number. You don't have to convince yourselves, and it doesn't ask for a more formal proof of that, but I mean, you can plug in numbers and see what happens, but it's essentially that's what's going on. So that's the first part done, I feel. Okay, what's going on here? Show that the differential equation blur describes a family of parabolas, each of which passes through the points 1, 0, minus 1, 0, and has a vertex on the y-axis. Okay, so here I feel is where the differential equation stuff comes in. So I've got dy by dx equals 2xy over x squared minus 1. Okay, so if we bring the y's over to the other side, we're going to have a 1 over y dy, and we're going to have 2x over x squared minus 1 dx, tidied up with an integral sign. And then I notice that the left-hand side is just going to become ln of y. Let's say we'll leave the constant till later. And then I realise that x squared minus 1 differentiates to 2x, so this just becomes the natural log of x squared minus 1, and then plus an arbitrary constant. Now that arbitrary constant I'm going to turn into, say, log of a, because that's also a constant. I can add these logs together, so it's log of some a times by x squared minus 1. And now that I've just got a log equal to a log, I can cancel these things, so now y equals some arbitrary constant a times by x squared minus 1. And clearly, when y equals 0, and we're going to assume that a doesn't equal 0, otherwise this is a trivial, it's just the x-axis, then that means x squared equals to 1, which means x equals plus or minus 1. So I know for a fact that this curve always goes through 1, 0, and 0, and minus 1, 0. And I also know, if I was to expand this, that this is going to be a U-shaped parabola that crosses at minus a, and it goes through 1, 0 and minus 1, 0. I mean, it clearly satisfies what the question's asking for. Show that the differential equation blur describes a family of parabolas which passes through the points 1 and 0, they all do, minus 1 and 0, and has its vertex on the y-axis. Well, if you really want to, you could say y equals, and then it's a lots of x minus 0 squared, because we're completing the squared, and then minus 0 squared, and then minus a. Then clearly it's going to have a vertex at 0 minus a. If you want to leave it in completed squared form, or you could differentiate it, I literally don't care. But yeah, I feel that's answered. Okay. Next part. Hence find the equation of the curve that passes through the point 1, 1 and intersects each of the above parabolas orthogonally. Sketch this curve. Now, orthogonal just means perpendicular, and it even says down there, two curves intersect orthogonally if their tangents at the point of intersection are perpendicular. So what that means is I need to find the family of curves that are perpendicular at all points to that. So I need to solve for dy by dx equals the negative reciprocal of this thing, which is minus, brackets, x squared minus 1 over 2xy. Fine. I'll redistribute that out, so the top becomes 1 minus x squared now over 2xy, and this equals dy over dx. I'll multiply by y to get y dy on that side. I'll multiply by x to get 1 minus x squared over 2x over here. This is a lot easier to integrate because y becomes y squared over 2 plus a constant, say. I'll leave it to last actually. Then 1 minus x squared over 2x. Well, 1 minus 2, oh dear, I've done it wrong. 1 minus x squared over 2x is going to be, now I can take a factor of a half out, it's going to be 1 over x minus x squared over x, which is just x. Oh, look, that's half of the integral of 1 over x minus x dx. Where have I seen 1 over x minus x? Oh, look. I know that when I differentiate this thing, I get this. So if I integrate this thing, I get back. So I actually have y squared over 2 equals a half of, what is it? Ln of x minus a half x squared. So ln of x minus x squared over 2, and then don't forget the arbitrary constant there. If I times everything by 2, I now get this. Okay, right, and the c would just stay as c because it's just an arbitrary constant. If you want, it's gone from c to c1, I don't particularly care. Now here's the problem. Here's the problem. Y squared, because it's a real number, has to be, you know, greater than or equal to 0. But I've just shown that this thing over here, with the aid of a sketch, is always in the negative region. Well, then clearly this plus c has to be bigger than, it has to be bigger than a half for it to make sense. And in actual fact, were we given something? I swear we were. It goes to the point 1, 1. Okay. So when y is, so it goes through the point 1, 1. So when y is 1, 1 squared is 1, and then ln of 1, okay, minus 1 squared over 2 plus c1. Well, ln 1 is nothing. Minus 1 squared over 2 is just minus a half, and 1 squared is still 1. I add that over, so c1 is 3 halves. Ooh, that's nice, because we wanted c to be greater than a half, and it turns out it's 3 halves. Great, so the whole thing's shifted up. So we now have y squared equals ln of x minus x squared over 2 plus 3 halves. That is my function that's always orthogonal to this branch of functions. So hence find the equation of the curve that passes through the point that and intersects each of the above parameters orthogonally. Done. Sketch this curve. Right, okay, so I'm going to copy this because I feel this is important. Da, da, da. Okay, so what's going to happen? Okay, so if y, all right, let's tackle y equals ln of x minus x squared over 2 plus 3 halves first, right? Let's tackle that first. So what's that going to look like? It's going to take this, oh dear, it's going to take this thing and it's going to move it up 3 halves. So minus a half plus 3 halves is going to be a 1. So it's going to be up here like that. And now this minimum is now at, this maximum, sorry, is now at 1, 1. Right. Okay, what does it mean to say y squared equals to something? Well, that means y is going to be the square root of stuff, so we just square root the y value. So the square root of y, the square root of this 1 is just 1 and minus 1. So there must be a similar thing down here at 1 minus 1. And now we've got a problem. What's going on? Well, in actual fact, we can't have any more these things being negative. It's not going to behave like that anymore. What's actually going to happen? Interesting. Well, do you agree that for a y value, say of say a half, and a y value of minus a half, they're both going to have a y squared value of a quarter. So what's actually happening is every y value is going to have a mirrored negative version of itself. So actually what's going to happen is it's going to do this. It's going to go like that, like that. So it's going to create this symmetric about the x-axis kind of heart shape, this cardioid. Not really a cardioid. I've not done that particular well. So I could have said symmetry about not x, y equals 0. Oh, does it want me to find... Oh boy. No, I'm going to leave it as that. Because if I wanted to find this point and this point, I'd have to solve ln of x minus x squared over 2 plus 3 over 2 equals to 0. That's not a nice thing to do. So I'm not going to do it. No. I'd have to use some kind of numerical analysis for that. And this is a non-calculator paper. So I'll leave it as that. So hold on, I will call this B and this A, and I'll say A and B are solutions to 0 ln of x minus x squared over 2 plus 3 halves. Solutions to x for, there you go. So actually, I've been a bit cheeky there, and I've just said A and B are the values such that, and then it's the solutions to that. I don't know what it is, but that's the form. Yeah. Cool. I think that's it. Is there any more? Two curves intersect orthogonally if the tangent is the point of intersection of perfect. No, that's it. Cool. So there you go. Hopefully you enjoyed that. And yeah, have fun.